minutes just to see if it works.
Okay, many people have been asking to give a more lower level and at the same time higher level description of what HPX is actually all about. And I will want to try to give you an overview. And since I have no idea what's actually interesting and what is too low level and what is obvious information for me but essential information for you because you don't have it, so let's do it more interactively and try to do more of a question-driven thing. But wait, where's Parser? He said you wanted to be here, you wanted to ask hundreds of questions, and he's not here. Oh, okay.
He didn't show up today. So
Huh?
he didn't show up today at all.
Oh, I hope nothing happened. I mean, he fell off the bike again?
That's what I was thinking.
Okay, well, okay. So let's see. HPX.
You're off the screen.
That's part of what I'm trying to figure out. Okay, HPX. And if it's not readable, let me know, okay? Then I hope I can zoom in some way. So what is HPX? This is still on the screen. HPX, if you go up from the hardware and from the operating system and below the hardware, then it's a library which is not part of the operating system. Some people sometimes ask me, what is the difference between an operating system and a runtime system, as we call it? The distinguishing criteria is that an operating system is running all the time on the machine. When you boot up the machine, the operating system is brought up, and when you shut down the machine, the operating system is shutting down. A runtime system is brought up as part of an application and is shut down when the application ends. So the lifetime of the runtime system of HPX is limited by the lifetime of the application, where application is just a normal executable on Linux. Steve. Does it work?
It looks like it. You've got two people watching. Ryoji Takahashi, who's a former GR student, and Joan Massot, who's also a cactus guy.
Did you tell them that?
I didn't tell them. They just saw it.
Okay, well, welcome to those who are online. It's unplanned. Is it with sound even yet? So everything's there?
I haven't gotten feedback from anybody yet.
Okay.
When they start commenting on that.
Okay. So HPX is a library, and it is part of the application where if you again go up from look at it from a layered perspective, it is below the application and between the application and the operating system. And this is kind of the API we expose from HPX, and we will talk about the API in a second, or during this talk today. HPX itself relies on the operating system to expose essentially a POSIX-like API. So any operating system which has some POSIX-like API can be used, and HPX can run on it. As you might know, HPX runs on almost any platform we have access to: Linux, OS X, Windows, Android. Somebody even made it work on the Raspberry Pi and things like that. So arbitrary systems. Okay, let's have a look at what HPX itself comprises of. And now we'll stop drawing it in a layered way. So whatever is above isn't necessarily above the things which are below inside HPX. So HPX is more kind of, you can imagine it as a flat structure which sits in between the application and the operating system. We have 4 parts in HPX which are essential. Let me just draw 4 boxes here. And as I said, there is no explicit layering between those 4 essential parts of HPX. First of all, there's a threading subsystem. Threading. Is my handwriting legible? More or less. Threading. What we call LCOs, which stands for local control objects or lightweight control objects, and is all about synchronization. How do you synchronize things? Synchronization. AGAS, which stands for Active Global Address Space. And AGAS is essentially, well, I'll say a word about all of those in a second. And the last one is networking. Networking, which has a fancy name of parcel layer. Parcel layer. And the name parcel comes from, stems from the parallax semantics, where a parcel is nothing else than a message on the network. You can think of it as a unit of information on the network. So threading is a subsystem where we have a lightweight threading system, and that's what I want to focus on today mainly. LCOs, as I said, is about how to synchronize threads and how to expose synchronization to the user. Active Global Address Space is a 128-bit virtual address space which spans the whole application across different nodes in the system, which allows us to move things around from one node to another without changing its address. And the networking layer allows us to do the networking and tie to various different networking technologies in HPX. I will not go into this too deeply, but just as a list of things, we have a TCP/IP binding today, we have MPI bindings, and we have InfiniBand direct bindings for the network. Others are in the works. On top of that, we have a module which is sitting somehow in the middle, which is tightly interconnected with all of the 4 here. A framework which we call performance counters. Which is a framework which allows us to extract arbitrary information from the application, the operating system, and the runtime system itself through a uniform interface. You can easily write your own, supply your own information sources to the performance counters from the application or from any metric you would like to measure. The important part here is that performance counters give us the information in a uniform way, which allows us to build tooling which is agnostic to the metric which we look at. I'd call it adaptive policies. And those adaptive policies are pieces of code which consume the performance counters, do something with the information they get about the system, like queue lengths, wait times, idle rates, hardware counters, memory requirements, well, various type of things, can make decisions and feed that information back into the system to change things adaptively at runtime. So you can look at certain characteristics at runtime, make some decisions, and change the distribution of data in the system, for instance, or the amount of parallelism used for a particular piece of code, and so on and so on. This adaptive runtime adaptivity is actually one of the major distinguishing things HPX gives an application developer, because you can adapt to runtime adaptivity. You can take into account things like, we talked today with Vivek and with Samuel about that in a distributed application context, you have to deal with things like phase of moon and the general weather outside, because all these things influence the performance of the application on the cluster. Just have a heavy network user running on the same cluster at the same time with your application, and all of the characteristics of the application just go through the window, because the application has completely different performance characteristics suddenly, which is completely outside of the control of the application itself. But you might still have means of adaptively adapting to that situation and still get the best possible performance. And for that, you have to be able to look at the system characteristics of your environment, of your system load, and so on, and make adaptive decisions, redistributing data, running on lesser cores, or whatever seems to be appropriate. Especially in context of very dynamic applications, where things are very dynamic in the sense that you can't predict where the action will happen, on what of the nodes in the system the action will happen. This is very important. An example would be a simulation of a hurricane which comes in from the ocean. And when you start the simulation, you don't know where the hurricane will go, because, well, it's a 5-day forecast, and only during the simulation you actually will discover where is the physics happening, where are the gradients the steepest. So you want to adapt your load distribution, your data distribution in the application, depending on which of the partitions of your data are actually related to the action in the simulation. So you want to do runtime adaptive decisions. This is one of those examples where that is very important. Okay, as I said, I want to talk about threading today. Let's keep that in mind. This is the block I will talk about. But before we do that, I wanted, if there are no questions here so far, I don't see any questions. But before I go and dive into the threading part, I wanted to talk about how a HPX application actually runs and distributed, and how you can envision that. Because I somehow have the impression that some people might still have trouble in understanding what's going on when you run an HPX application and distribute it. So when I talk about running an HPX application and distributed, I mean running it on a cluster. You have, I don't know, 32 nodes or 1024 nodes, and you run your application on this amount of resources. So let's just assume we have node 1, node 2, and node K. And on each of the nodes, I have my own operating system. And interestingly enough, on a cluster, these operating systems don't know anything about each other. So each node is completely independent of the other node, and the operating system provides services for communication between the nodes, networking. Or they give you the local environment your application is running in, so memory allocation and so on and so on, are satisfied by the local operating system. What then is happening is that when you run your application, which you usually do on a cluster using Slurm or PBS or any other batch allocation system, then what's happening is that the batch scheduler runs the same executable on each of the nodes. So you run executable here, you have an executable running here, and you have the same executable running on that other node. And if you do that with MPI, then the MPI library you link with somehow magically establishes the contact between the instances of your executable, which runs on different nodes. And the very same is happening when you work with HPX. So HPX is linked to each of your instances of the executables. And when you run your distributed application, each of the nodes gets its own instance of the HPX library loaded. But once HPX, the application has run, these guys start talking to each other under the hood without you doing anything and coordinating things. So each of the localities, what we call a locality, this is locality 1, locality 2, locality K, knows about every other locality in the system. So it knows exactly how many other executables are there which are kind of part of that application. And AGAS, the global address space, which is implemented, logically spans a global view of the overall address space and pretends that you can talk to each of the parts of the nodes, and you can access data on each of the nodes without even knowing whether that piece of data is local to you, to the code which is accessing that data or not. Yes, Steve?
What's the current status of AGAS? Is it running on a single node? Is it like a central server, or is it distributed now in some way?
So I don't know if I just repeat the question for the camera. The question is AGAS running on a single node or is it distributed? The answer is both. AGAS itself consists out of 4 parts, and let's not go into too many details, but 2 of those parts are distributed databases, and 2 of those parts are on one node only, on node 0 essentially, or node 1. The reason for that is that the 2 parts which are not distributed are necessary essentially only during bootstrap. So whenever you build up the application, you have to distribute or make sure that the same things have the same name on all nodes. And this is a one-time process, and that is done through that single point of contact. But the actual address space, which means the mapping from the global address to the local address, is a distributed thing. Our measurements show that AGAS itself and the networking traffic and the overheads introduced by AGAS are neglectable. You essentially have no measurable overheads from using AGAS in the system, which is kind of an interesting result. Hey, Parson, we're waiting for you. Sorry.
Waiting? Oh, sorry.
No, we didn't wait.
Well,
We were hoping you'd show up.
we were wondering where you are. Okay, so that's AGAS. And in the end, HPX is loaded as part of the address space of each of the nodes. But since the localities talk to each other, you can think of the AGAS layer of one uniform thing, which is accessible from all of the localities. Does it make sense?
Yeah.
You launch an HPX application, and that might be interesting to you, essentially very much the same way as you would launch an MPI application, either through the batch system. Some batch scheduling systems already use MPI run under the hood to launch things. Others require you to use MPI run explicitly, especially when you use the MPI network bindings, and the MPI run is just the way to go. For PBS, you have to use other tools and so on. But normally you just run it in the same way as you would do that with MPI, plus minus some variations. Okay. This is just to give you a context what HPX is all about and how it integrates with the system. So let's talk about the thread system, thread subsystem, because that is what many people have been asking about, thread subsystem. Okay, so let's start with the simple question: what is a thread? Any ideas? How would you define a thread? What are the defining characteristics of a thread?
A thread is how the OS controls what process is running currently on the core.
Okay, it's what controls what is currently running on a core. Okay, other opinions?
Threads share memory.
Threads share memory, but you don't want
You might not want that to happen, but that's what they do.
threads share memory, yeah.
A stream of computation.
Very nice. It's a stream of operations, right? Essentially opcodes. So it's a sequence of operations you want to perform on a particular code. Add two numbers, load something here, store it there, whatever the underlying opcodes are.
Memory states.
Memory state. Let's call it thread state to be more general.
Yeah.
Thread context. Let's call it thread context. And memory is one of the parts of the thread context. What else do we have in a thread context?
Current part of code is
The
The
program
registers
counter.
you're saying?
So the register which contains the address of the next operation to be executed. Program counter. What else?
The state of the thread.
State is the state of the thread. What is the state of the thread?
Whether it's queue or
That's state. Okay.
Yeah.
Oh, let's put that separately. State. Program counter. The stack is usually part of the context. And
But isn't, so you mean, so stack is memory, right? So it is
Yeah,
a sub portion of memory?
yeah, in some sense, yeah. It's just a specialized way of representing the call stack, and that gives you kind of the state where the thread currently is in.
So by memory you mean heap?
Memory, well, static and dynamic. Static plus dynamic memory.
Mm-hmm.
That could be heap, that could be some static variables, or thread local variables, or whatever you're
Global, yeah.
talking. Program counter and registers in general, right? The hardware registers we have in our core, which have some values, which is part of the context. Yeah, and state, thread state. So what, and this is actually a very important piece, because it tells us whether the thread is currently running, whether it's currently suspended, or what's currently going on with that thread. If you look at it that way, in that way, essentially what we can do, we can say, or let's ask the question, what information do we have to store in order to represent the whole state of the current thread, of the whole thread? What is the piece of information we need to store when we want to save and be able to resume or suspend the thread and resume it again? Essentially what we need is, we need to store all general purpose registers in the core, because there's some addition which is currently, the result is still in the registers, and if we disrupt that thread and we want to start doing other things, we have to remove all that information from the core and replace it with some other information. And when we come back later on and want to resume at that point where we left off, we want to restore all the core state in a way so that the thread can continue running without losing any information. So that is probably the general purpose registers. And it's the special registers like program counter, stack pointer, and so on and so on. Luckily, this information is about, well, in HPX we store, I don't know, 8 perps, let's say 64 bytes or something. So 64 bytes or about 100 bytes are sufficient to take a snapshot of the current state of the core and store it somewhere. And when you come back, you can reproduce the current state 100% and continue working. Okay? Okay, good. Okay. So in HPX, the thread subsystem is responsible for creating threads, destroying threads when they are not needed anymore, and the most important thing is the system schedules the threads. If you have millions of those guys, and we have millions of threads in the system, you want to be able to decide in what sequence all those threads are being executed, right? Because we have only a handful of cores, and well, definitely we have less cores than we have threads. If you have 10,000 or even 100 threads, it's still more than we have cores, so we can't run all of the threads at the same time. So we have to make decisions which of the threads are being executed in what sequence and at what point in time. And in order to be able to do that, a thread has a state, so that the scheduler, which is responsible for scheduling things, for making sure that threads are being executed, so that the thread scheduler knows whether a particular thread can run or not. Right? A particular thread can run under two conditions. A, when all the preconditions for it to run are satisfied. Well, if the thread is supposed to add two numbers, then you better don't run that thread if the two numbers are not available yet, because they are being computed still. So you want to wait until all values which are necessary, or at least some of the values which are necessary for the thread to execute are available. Otherwise it doesn't make any sense, so that the data dependencies are being observed. The other thing you want to make sure is that you have a computational resource you can run the thread on. So if you don't have a core available, because all cores are busy, then you can't run the thread. And if these two criteria are fulfilled, then the scheduler can consider running this thread, making this thread active on the current core. So to understand that better, let's have a look at a state diagram of states of the thread. Or just think about what are the lifetime, what happens during the lifetime of the thread. Well, a thread starts off as being in some init state, right? You create a thread, you say, here's a function, I want to run that function, make sure it runs on a thread at some point. So the init state is essentially just a description of a thread. It encapsulates information which the scheduler will need in order to create a thread, to run it, to make it work. So in most of the time, this encapsulates just the function you want to execute. And by function, I mean C function, like you know it from C or from C++. It's just a normal function. And the arguments you want to pass to that function when you run the thread. And that, on the other hand, tells you that in HPX at least, anything which is a function, be it a global function or be it a member function of an object, can be run on a separate thread. Because as long as you can take an address of the function and get all the arguments you want to pass on when that thread is running, you can just schedule that thing as a thread. The first thread state, which is the next one after you create a thread in an init state, is what we call staged. This is still just a thread description, namely the function and the arguments, but it is already bound to a particular scheduler where it might run. So the init state is just a thread, independent of anything else, or just a description of the thread. Staged means it is sitting somewhere, and the scheduler knows that this thing can be run at some point in the future. Well, the scheduler runs out of work and looks for new work. So what does it? It looks at the list of staged threads, and it creates those threads and in two ways. Either it creates a thread in pending state. A pending state, a thread in pending state means that the thread is in principle able to run. All the preconditions are met for that thread. The other option is that a thread is created in suspended state. Suspended means the thread can't run because some of the preconditions are not met. So a suspended thread is essentially just sitting there as doing nothing. It's just a piece of memory where all the information is stored and is sitting in the side. A pending thread, on the other hand, is added to a queue of threads to be executed. And I will talk about the queuing system a bit later. But this pending thread can run as soon as a core becomes available for it to run. So that means that from pending, the thread can go into active or running state. And the step from pending to active happens when the scheduler runs or has to decide, or some thread stopped running on the core is available, and the scheduler decides this particular thread should run now. Then it is placed in running mode and is associated with the core, and the core starts executing code related to that thread. At some point, the running thread is done running because, well, you run to the end of the function and you exit the function, and that means that the thread is now terminated. Terminated, well, something like that. And a terminated thread obviously can't run anymore. It's done running because the function just ran to completion and you exit it. And that means that the thread itself can be deleted.
And it's all the information of that thread is done. Like
Well, if the function is done running, well,
Yeah,
then
so-
you don't need it anymore, right?
Yes.
Then the thread is done running. The other thing which can happen is that a thread suddenly becomes ready because all the preconditions have been met. And that means that the thread which was suspended before now is placed into pending state and is put into one of the queues so that it can be executed later. And what also can happen is that a thread which is active suddenly hits a synchronization element, which tells it, hey, you now have to wait for some value to be available. You now have to wait for a resource to become available. It could be a mutex, right? Or it could be a fuse, or it could be any of the synchronization elements, which tells the thread that now it has to wait for that particular synchronization element to become available, for the value to become available. And since you don't want to sit on the core and spin and waste cycles until that event might happen, we suspend the thread. We remove it from the core, put it in suspended state, and so that the core becomes available for other threads to be executed. And this is a simple transition from active to suspended. And whenever that condition has been met, it will get into pending again and will wait for its turn to be executed on the core. So a thread actually can circle here many times before it gets terminated. Okay? Fairly simple scheme actually. It's nothing difficult to understand. But I really wanted to make sure that we understand this scheme so that all other discussions we will do kind of make sense. Questions? No? Good. So our threads in HPX have actually 1, 2, 3, 4, 5 states. And if you look at the code, there's a numerator somewhere, and the numerator is called thread state, and it will have these thread states. And they are, well, you have seen it probably somewhere if you have browsed through the code. Very simple scheme. The transition between the states is performed by the scheduler. So the scheduler is responsible for changing the state in the thread. And if things are a bit more complicated, especially in that transition, but I will talk about that in a second, when we do when an active thread either gets into suspended or terminated state. But I will talk about that in a second. In general, this is what's going on. So the thread itself doesn't do anything. It really has just a variable which stores in what state it is currently in, and the scheduler sets that variable and makes sure that the thread is put into the proper context. Okay? No more questions? Great.
What's a thread description?
Hmm?
What's a thread description?
A thread description. What is a thread description? Well, a thread description is what I was trying to get to here. A thread description. Hold on. You mean what I was saying here in the context of
No.
the init state? or in general, what is
Yeah,
information
yeah.
stored
Yeah.
to represent a thread? Well, it's the set of registers of the core, which represent essentially the context of the execution of the thread. Where's the program counter? Which operation is next to be executed? And so on and so on. What are the current set of registers? What is the stack state and all that information? Plus a variable which contains the state of this thread, which tells you it's pending, it's active, it's running, whatever. And a pointer to the function, which is the initial entry point, and the arguments which have to be passed to the thread in the beginning. That is essentially the thread description if you want. That is all the information you need to recreate the thread from scratch if you need to, or to suspend it and resume it afterwards at some point, and so on. Okay. So let's talk about the scheduling. How does thread scheduling work in HPX? Scheduling, or scheduler. The big picture is the following. Excuse me. Whenever HPX as a runtime system is started, is brought up, an application is brought up, it creates a certain amount of, or it takes ownership of a certain amount of cores in your system. The amount of cores and which of the cores it uses is defined by command line options. And I will talk about command line options a bit later. But at minimum, you already use, when you have run an HPX application on a single node, you probably have done --HPX colon thread equal to, I don't know, 16 or something. So you tell HPX how many cores to use to run the code. There are again nuances when you run HPX with a batch scheduling system or without a batch scheduling system, but that's nuances. We can talk about that separately. So what happens is, if you tell it to run on 4 cores, it will create 4 operating system threads. And I have to make that distinction between an operating system thread and an HPX thread, because these are very similar but very different things. By operating system thread, I mean the object which is created by the operating system to manage time slicing and all the operations an operating system does in terms of executing and of core ownership. This probably contains very similar information to what I listed, set of registers and entry points and all of that stuff. But a operating system thread HPX creates one of those operating system threads per core it should run on. And it also tells the operating system that this particular thread of execution should run on this core only. Because operating systems, they tend to be, or tend to try to be intelligent, and they start moving things around in a local node, depending on the load on the system. Because operating system is likely the benevolent mother trying to make it good for everybody. An operating system tries strives to maximize overall average throughput through the system. So if you have 5 processes running on the same operating system, then it tries to share the resources in a way which is kind of fair so that everybody gets its turn and so on and so on. And that might include that these threads have to move to a different core because some cores are in use currently. HPX tells operating system not to do that for the cores which are in use. That means that a particular thread which is owned by HPX then will run on this core only and nowhere else, which is very good because that allows us to control cache coherency and other things, and we can be sure what will happen on each of the cores and we can control what's going on. Each of those threads now starts executing what we call HPX threads. And an HPX thread is really nothing more than a C function or a C++ function. So just think about it. Whenever I say HPX thread, think about it as a global function in your code, nothing else, or Fortran function if you like it. Doesn't matter. And the scheduler has a queue of those things to execute. So essentially a list of those threads which are in pending state. And we'll take the next available one from the queue and we'll just run that function. And when that function runs to completion, it grabs the next one and executes the next function, and so on and so on. So it constantly runs HPX threads, all of them representing a particular function, until that function runs to conclusion. And this is a big difference between an operating system thread and an HPX thread, that an operating system thread relies on time slicing, on preemptive scheduling. The operating system, I don't know if you know that, assigns a certain time slice to each of the threads in the system, to each of the operating system threads in the system. So each of the operating system threads gets 20 milliseconds time slices, and when the 20 milliseconds are over, that thread is just ripped off the core and another operating system thread is allowed to run on the core. That's what the operating system does. So, and HPX threads are never preempted. They always run to completion. So in order to get a HPX thread off the core, it has to either suspend actively or terminate actively. It has to give up the core voluntarily. This is a big difference. That also has the implication that you don't want to have a extremely long-running HPX thread which runs for 5 minutes. A function which runs for 5 minutes, you don't want to run that as an HPX thread, because that will grab the core, will run it for 5 minutes, and nothing else can happen on that core. The flip side is that HPX applications are usually written in a way that each of the threads you create in HPX are very short-lived. Short-lived as in 100 microseconds, a millisecond. So very, very short-lived small functions which run only one task, execute one task, and then they exit and terminate, and the next thread can continue, and that allows to very nicely load balance and so on. Okay, so let's look at the scheduler. So as I said, what we have, each of the cores, and this is kind of the scheme for one of the cores only, and that happens on each of the cores HPX is running on. So for one of the cores, we have a list of pending threads. So those threads which are in principle can run because all the preconditions for that thread are met. All values have been provided which are needed in order to run that thing. All arguments are available. This is most of the time a simple first in, first out data structure. So the thing which was put in first will be extracted on the other end first. It's like at Walmart at the checkout, right? People who come first are usually served first. I mean, it doesn't work always the same way. Some people have higher priority for some reason. But just for simplicity, let's think about it as a first in, first out data structure. Oops. No, I'm screwed. I have no idea what I should do.
Chris, are you listening?
Huh?
I said, Chris, are you listening?
Chris?
Oh, Rob.
I don't know what I should do. I'm still,
I don't know why they stuck that one.
I don't know what happened. Just decided to stop doing that.
In full screen, you can swipe across the touchpad with 2 or 3 fingers.
With 2 or 3 fingers, okay. I mean, I have no idea what to do with that. Oh, there we go. Thank you. We solved it. We found it.
Okay.
It just decided on its own to go away.
To minimize.
Okay. Okay, cool. Okay, so a list of pending threads which are inserted at on one end, and the scheduler grabs it from the other end. So whenever a core becomes available, the scheduler looks at that list, grabs one of the items on that list, which is essentially a function and the arguments, and starts executing that. So you can think of the scheduler being a single operating system thread which runs in a loop. It's the operating system thread runs in a loop, and the first thing it does, it grabs the next one from the list. Grabs the next HPX thread from the list, does a context switch, and I'll tell you in a second what that is, and starts executing that function. Which is the function we want to execute as that thread. And when that function runs to completion, it comes back, does another context switch, back to the state it was before, and closes the loop and grabs the next thread. So that's all what the scheduler does. It runs all the time on a single core. It's an operating system thread which runs a for loop essentially, grabs the next thing, executes it, when it comes back, grabs the next thing, and so on and so on. And it does that all the time. And that might explain why, even if you don't have any work to do in HPX, why it still shows 100% system utilization on that core. Because that loop runs always. And even if that thing is empty, that queue is empty, it will still run there and will wait until things appear in the queue and will execute those things. There means we can relax it a bit, and it's a bit relaxed, but often you see that it still shows 100% system utilization, but nothing is actually going on. But this is because the scheduler is running that for loop constantly. And that is by design, just to reduce latencies. We could put that thread to sleep, but then when the next work item appears, we would have to wait for the next operating system time slice. Because that thread is still operating system time sliced. It gets only 20 milliseconds from the operating system each time it is executed. So we would have to wait at max 20 milliseconds before we actually could execute the work we've been waiting for. And if you compare that to the length of the HPX threads, which are in the millisecond range, 20 milliseconds is a huge latency. And for that reason, we let it just run and use the system to its maximum. Yes?
So just to make sure, an OS thread is in charge of all these threads of the HPX, right?
Yes.
So, and then that OS thread is locked to the core that you want. You lock it so in
Yes.
order not to go around.
Yeah, so that the operating system doesn't move it to another core. Yes.
Okay. So
And what I show here happens on each of the cores HPX owns. So if you have 10 cores, then you have 10 operating system threads, 10 lists, and each of the cores is doing the same thing at the same time, concurrently. Okay? Now a word about what is a context switch. A context switch means that all of the registers in the core are stored somewhere, and a different set of registers is loaded into the core. So essentially it switches from one thread to another. In that context, you can think of that as being one HPX thread, and those guys are the other HPX threads, and it just jumps back and forth between those threads. Another term is coroutines. So if you read about coroutines, this is a typical coroutine scheme, and that is what I don't know, Steve, if that was what your question actually is, how, or I expect you know that it's working that way, right?
I know it works that way. I've always had trouble with the details is the problem.
Well, we can look into the detail as well. Let's stay at the higher level at this point. And if it's too high level for you, I apologize. It should, just to explain the whole thing. So a context switch is essentially nothing else than taking all these registers, storing them somewhere, and getting another set of those registers and shoving them into the core and keep running. And when the context switches back, then the registers of this thread are restored. So from the standpoint of the scheduler, nothing happened. From the standpoint of the scheduler, this actually looks like a function call. It calls a function and it exits from the function. And the interesting thing is that here, after the context switch, we run that function, and when it comes back, it looks like it exits the function the scheduler was calling. So from the standpoint of the scheduler, it's a normal function call, and from the standpoint of the thread, it is as if it was called as a normal function. But still, all the complete register set is exchanged. And the important part why we do that, you might say, hey, why do you do that? Why don't you just execute that function, be done with it, right? You could do that without a context switch. Just call it and by all means. But what we want to be able to is that these functions are being suspended, as I said in the beginning. When this function hits a situation when it can't continue because it has to wait for synchronization, for a value, or for a future, for a mutex, then we don't want to spin here, but we want to be able to give up the core and run other things on the core. So what this function can do is it can suspend in the middle of it, somehow return here and somehow come back. Right? Suspension just means you stop where you are. We store the state of the registers at that point, somewhere deep in the middle of a function hierarchy. And at some point later, when time is right, we come back and continue at exactly that point where we left off. And from the standpoint of the function, it looks again like a function call. You just call suspend. Right? When you call suspend here inside that function, it will exit the context, and when it comes back, it will return from the suspend function. So what's happening is that here are context switches as well. Very similar context switches to those, but the difference is that if we have the final context switch, the stack is empty because we have returned from all the function calls, we exit our function, we have nothing on the stack anymore. But in the middle of it, we have a stack state which stores all the function call hierarchy and all the parameters to all the call functions and so on. And that state has to be retained. And that is the reason why we have to do the context switch, because each of the threads in HPX has its own stack segment associated with it, its own. And we wouldn't be able to suspend a function if that wasn't the case. Because suspension means store the current stack state as it is, so that you can come back and return. You know, you don't want to unravel the stack and return from the topmost function. You want just to exit low down and come back and continue and do other things. That's why we have to do that context switching, so that we can replace the stack essentially whenever we execute a function in that context. And this makes that function execution actually equivalent, semantically equivalent to a thread, because it has its own stack space. And that's why we call it a thread and not a task or a function or whatever. That's why this thing is called a thread, because it has all the properties of a operating system thread or of a thread as we know it. Okay? I know it's a bit confusing, but it is why we chose to do it that way. Okay, I said a thread runs to completion, and you can't execute other things on the core as long as that guy is active, obviously, right? Because it has to return before the next one can be selected. It's just one thread of execution, and it's doing nothing else than executing that function. Wait, when the function returns, it does the next thing, and so on. How does the scheduler know whether that context switch or when things returning here, whether the function ran to completion or whether the function has to be suspended? That's the question we have to answer. And the only guy who knows whether it has to be suspended or whether it ran to completion is the thread itself. Because if the thread exits its context through a suspend function, then it has to be suspended. When it exits the context through the terminate, through the end of the top level function, then it has to be terminated because you're done. And this is done through a return value. So this function has a standard return value, which is the new thread state. The thread has to be put in when it returns to the scheduler. So each of the HPX threads, when it exits, when it comes back to the scheduler, tells the scheduler what to do with the thread next. It will return the thread state. The current thread has to be transferred to. And the possible values are terminated, obviously. In that case, the scheduler will just get rid of the thread and will delete it. It can be suspended, in which case the scheduler will just put that state, will just leave that thread alone. Or it could be pending, which is interesting. So you could even return pending from that function, in which case the scheduler will put it at the end of the queue and will immediately re-execute it, which is sometimes useful if you really just want to give up control for a very short period of time, because you want other things to execute before you continue. Then you just tell it, oh, keep me in pending, reschedule myself, and then that thread will be executed again. Makes sense so far? Okay. So this function, the actual high-level entry point has a certain prototype. It is expected to return the thread state to the scheduler. Now, you will never see that in actual code, because in actual code you can execute an arbitrary function which returns anything. But this is some magic which happens inside HPX, and we can talk about that another time. But in principle, the outermost function executed always will return the thread state to the scheduler. That's a piece of information you might not have known. So I hope at least that I can give you something, Steve. Okay. Okay. Another thing I want to talk about is work stealing. So, as I said, let's say we have 2 cores or several cores. Each of the cores has its own list of tasks. And each of the schedulers here does its thing in the same way as I explained it. What happens if the scheduler runs out of work? Meaning if that queue is empty. Then our schedulers are written in a way that they start looking to the neighbors. And they will look first to their immediate neighbors and say, okay, do you have some work? Yeah, you have 300 tasks. Let me steal 100 of those. It will grab 100 of the tasks from the end of that queue and transfer it here and keep working. And every of the core is doing that, which has the effect that we have a very nice load balancing across the local node, because you can essentially feed all the work to one of the queues. And the cores will distribute them in a very nice way, evenly across the whole local node, because whenever one of the schedulers runs out of work, it will start stealing work from the neighbors. So
is that an option, or?
No, that's just built in. That's
like what happens to that coherency of the data in the
well, cache coherency, you mean, or what do you mean?
Memory and
Well, it's everything in one node, inside one node. So nothing happens.
okay, because you said in the beginning that cache coherency.
So the cache between the cores different. So there's hardware's managed to do cache coherency between those. My answer?
Well, I'm not quite sure what you're asking.
Because in the beginning you said that all the data are just contiguous, and then we don't have that like.
Well, the global address space, you mean the global address space I was mentioning?
Yeah.
The global address space spans nodes, it's across nodes. But the load balancing, that work stealing, happens only inside each of the nodes. And there we have a local memory, right?
Mm-hmm.
I should have said that HPX is written in C++, as you know. So the code itself doesn't know anything about being distributed. The code itself obeys to the rules of C++, or C, or Fortran, whatever code you execute there. And that means that the code itself is built under the assumption that it runs in the C++ memory model. So it has a local memory in the node it's running on, and it has access to that local memory through the normal means of allocation of memory and array allocation and pointers and everything. So it's normal code, which is just C++ code. Stealing a task from one core to another core doesn't make any difference, except that you disrupt the cache coherency between cores when they are far apart, when they are different sockets. So you have to be a bit careful there, and you have means of controlling that. But you definitely disrupt
Okay,
cache
so this is
control.
all happening in one socket, and we are not dealing with that NUMA.
Right.
No.
As long as
Okay.
that stealing is happening only inside one socket, you don't even have any NUMA
Oh.
problems. But you can still steal across sockets, and then you have to deal with that. But you can control that. What
Okay,
gets stolen.
that's an option.
No, you can control that.
Oh,
Definitely.
You can control whether work gets stolen across new mother names?
Yes.
Okay.
It's called executors.
Okay.
It's an abstraction we have in HPX which allows you, on top of the underlying general scheduling mechanism, you can partitionalize the cores from the API level. You can say, I want to run this parallel for loop on those 4 cores. And then it will run only on those 4 cores and will never be stolen to any of the other cores. So you have API means of constraining algorithmic sections or code sections in your application to run on a particular subset of cores only, which will prevent stealing across a new domain. But by default, it will just distribute it, and so it will work by default, but it might not be optimal because you might run into the cross NUMA domain issues. But we have definitely means of controlling NUMA awareness and this kind of thing, and we can talk about that another time perhaps. By the way, Steve, you were right. I'm just babbling way longer than I anticipated.
I told you it would be, an hour would be no problem.
Okay. Oh, it's more than an hour already. Okay. So this is happening. This is what's happening in the scheduler below. Any questions about that? And that might be interesting only just as a kind of contextual information for you when you look at HPX. That might never be something you are directly dealing with. It's just nice to know what's going on. One thing which is probably important in that context is synchronization between threads. If somebody, most of you probably have worked with mutexes. So mutex is a data structure which allows you to protect a certain region in your code from multiple threads being executed at the same time. It makes sure that only one thread executes a certain region in the code. And it's doing that by having an atomic variable, and the first thread grabs that or sets that atomic variable, and any other thread which comes along will wait for that atomic variable to be released. And if the atomic variable is set, the next thread will see that and will suspend itself. Now the problem is that you can have a mutex on the operating system level. And the operating system normally, or at least the libraries, give you a mutex which works on the operating system level. And that means that if an operating system thread hits a mutex and has to wait for it, it will suspend itself on the operating system level. It will essentially terminate the current time slice prematurely. It will tell the operating system, hey, I'm done, I have nothing more to do, just run something else. So the underlying operating system thread will be suspended. Whereas, if you do that on an HPX thread here, if you grab a operating system mutex here, that means that the whole scheduler will be suspended. So no HPX work will be performed on that core anymore until that operating system mutex is satisfied. And the moratorium is never use an operating system mutex on an HPX thread, because that will disrupt the whole scheduling system. It will stop this core to be available for HPX. Because the thread itself is put to sleep. The operating system is not running that thing anymore. Okay? And that's the reason why HPX has its own subsection for synchronization, because we have our own synchronization primitives, our own mutexes, our own condition variables, semaphores. All these different kinds of synchronization variables or synchronization constructs you might ever want to use are implemented in HPX separately. And the difference here is that whenever a HPX thread uses an HPX synchronization primitive, which requires for the thread to be suspended, it will suspend it through the context switching mechanism instead of through the operating system. So it will keep the scheduler available to execute other threads, but will not suspend the whole damn thing. So that's very important to have in mind when you start dealing with low-level synchronization things, that you shouldn't grab a standard mutex, for instance, or a p-thread mutex, or one of those constructs, because that disrupts the whole concept we have. That's what you get when you run a scheduler on top of a scheduler. And because operating system doesn't know anything about our scheduler, and our scheduler doesn't know anything about the operating system scheduler. And the reason for that is that the Linux developers have decided that nobody in the sane mind would ever want to talk to the Linux scheduler or vice versa. So they just deliberately prevented that from happening. In Windows you can do it very nicely. They have a very nice interface to coordinate the schedulers, but on Linux it doesn't work. So this is just a note of caution for you to understand that there are caveats to this kind of system. On the other hand, just to give you another benefit of the scheduling system we have in HPX, since the context switches we are doing between the threads are not done in the Linux kernel, the context switching is about 100 to 1,000 times faster than whatever the operating system can do in terms of context switching between threads. So when a context switch in the operating system essentially requires you to wait for the end of the time slice. So you might have to wait for 20 milliseconds before the other thread is able to run on the core. Whereas in HPX, a context switch takes about 400 nanoseconds. The whole lifetime of an HPX thread is life cycle is about 1.2 microseconds. Create a thread, schedule it, run it, delete it. 1.2 microseconds. So it's very efficient, and you can create HPX threads without even thinking about them, as long as you have a reasonable amount of work. I mean, if all what you want to do is adding two numbers, then an HPX thread still will kill you because of the overheads. Because adding two numbers is, I don't know, less than a nanosecond. And if you add 1.2 microseconds to add two numbers, well, it doesn't make much sense. But as long as you have work which is in the range of 100 microseconds or above, you will not notice any overheads imposed by an HPX thread. Okay, the last thing I wanted to tell you is how does that tie into the HPX API? How do you create a thread in HPX? And creating a thread in HPX means creating the data structure representing the state and everything else. And if it's pending, putting it into telling the scheduler, here's a thread to execute. And the rest will be done by the scheduler. The API, the lowest level API in HPX we have is a function which we call HPX : apply. Apply gets the first argument as a function, an arbitrary function, and a set of arguments. And apply will run f on a new HPX thread, passing these arguments along to the function. So essentially, apply will make sure that the function will end up being one of the HPX threads at some point in the future. You can't define when that will happen because it will end up on the end of the queue, and it depends on the amount of work which is available, and so on and so on. Apply will not return anything. So you have no means of figuring out whether the thing has run or not. It's kind of fire forget. All what HPX makes sure is that this function will be executed before the application terminates. End of story. Kind of useless, because most of the time you want to synchronize with the result. You want to be able to get the result. Well, if that function returns something, right? Let's say this is a function int foo and it takes some arguments, you want to get at that int. You want to get that result back to you. And for that reason, we have another API which we call async, which takes the same arguments, but this one returns you a future to the type of whatever that function returns. So if that function returns int, then you get a future to an int. If that function returns double, then you get a future double, and so on and so on. And a future is a construct which represents a result which has not been computed yet. So it's an object which kind of is a handle to the result which you will get somewhere in the future. And in order to get the result, you call f.get. And it will give you the result of whatever the function has returned. Async schedules foo on a new thread, so it will be concurrently executed at some point, but it gives you immediately a future representing the result of whatever the function will return in the future. And it will give you a means of accessing that value.
Is there a difference giving the async with the bracket format versus the first parameter?
Async was a bracket format.
Where you say,
Oh, okay, yeah, the triangular
yeah,
bracket.
there's no difference.
So the question is there a difference between this async and the async you might have seen?
Mhm.
Yes.
Okay.
The difference is that this async, which takes a function as its first argument, is a local only operation.
Okay.
It will just schedule this function locally. End of story. Whereas the async with angle brackets works with actions, which is a means of invoking remote functions, possibly remote functions.
Okay.
So the name is the same, the semantics are the same. The difference is that that one is really just local. And since we are talking about the thread manager, I'll just.
Mhm.
So this is the distributed version. Okay, f.get. So if you call async, you can keep going and doing other things which are unrelated to the results you get back from foo. But at some point you might want to access that result, and at that point you call f.get, and it will give you the integer. And get can do two things. If at the point of invocation of get, the value has already been computed and returned because the other thread has run to completion, then get will just give you the value. But if at the point of calling get, the other thread has not run to completion yet and the value is not available yet, get will internally suspend and will suspend the current thread. It will only return once it has been resumed because the value has been delivered. So you don't see the suspension at all. You just do .get, and get gives you the value whenever it arrives. But .get suspends the thread, and that means that the core which was running your function is now free to do other things in the meantime until your return value from your function arrives. And that keeps the system nicely going without blocking anything. Okay, so this are the two most important functions to remember. For people who know the C++ 11 standard, you probably know that there's something like a std thread object, which just represents a operating system thread. And what we have is a HPX : thread, which exposes the same API as a standard thread, but just creates an HPX thread instead. And actually apply an async, use HPX thread under the hood to run that function. The way you do it is by passing the function and the arguments as to the constructor of thread, and then you say t.join when you want to wait for the thread to run to completion. This is a bit different API, but you can read about it in the C++ 11 standard. So that's C++ 11 for you. And since we want to be very compatible to C++, we created an object which exposes the very same API as the standard thread object. You can read about on the internet everywhere. Okay, other questions? Oh, great. And I'm done. Time's up. Thank you.